Welcome back, everybody. We continue with our second speaker today, Mattia Zanella from University of Pavia, and he's going to talk about uncertainty quantification for kinetic equations of emergent phenomena. Thanks a lot, Mattia. Stage is yours.
Okay, thank you. First of all, I would like to thank the organizers. I would like to thank Jingwei and Jose for the very kind invitation, and I'm very happy to speak about this recent advancement on uncertainty quantification for kinetic equations. So today I will revise some recent results about numerical approximation of kinetic equations in the case of a random input, and all these works have been obtained through joint works with Jose, with Giacomo Di Marco, Andrea Medaglia, Giuseppe Toscani, Andrea Tosin, Lorenzo Pareschi, and Benoit Pertam. So first of all, I will introduce a bit the problem with a special focus on Boltzmann equation. And then I will switch my attention to new models of kinetic type with application to mathematical epidemiology, where the concept of randomness is strictly present, I would like to say. And then I will draw some conclusion. So let's start. What do we mean with uncertainty quantification for PDEs? So typically in application, what we have is some statistic about the inputs of a model, and then we have our model, that is the PDE, and as a result, we obtain some uncertain solution. So an ensemble of solutions of our PDEs, and from which we have to obtain some information that has to be robust enough. So the increased interest on uncertainty quantification for PDEs is a consequence of three main factors, I would like to say. So the availability of data, the increased development of high performance computing technique, and the ability of construction of new algorithms for this kind of problems. So as I said, the point is to construct some strategy, some numerical strategy to obtain an accurate evaluation of some quantity of interest. And then I will enter more in details about that. So let us focus on the Boltzmann equation. So as many, everybody knows what is the Boltzmann equation in the audience. So we have a distribution function that depends on space, velocity, and time, and on some, in this case, on some random input that may affect, for example, the initial condition of our problem. And epsilon is the Knudsen number, and then we're supposed to know the distribution of the random vector Z. Z is the source of uncertainty, so it can be d-dimensional in general. So Q is the usual Boltzmann type collision operator that reads as follows, and the particles undergoes binary collisions that are sketched here according to Newtonian mechanics, and then the kernel B that has been introduced here depends typically on relative velocities of the two interacting particles. We have Maxwellian case for gamma that is equal to 0, or gamma equal to 1, it is the R-sphere case. For gamma equal to 2 is a very R-sphere case. So in the realm of uncertainty quantification for Boltzmann equation, we had several advancements in the recent years, the last decade, I would like to say. So we have three macro technique, I would like to say. So the first one is stochastic hierarchy methods. Stochastic hierarchy methods require the knowledge of the distribution of Z, of the uncertain input. And applying this kind of technique, what we have is spectral accuracy with respect to in the random space. But the point is that stochastic hierarchy methods are quite costly and suffer from the curse of dimensionality. So the second group of techniques are multi-fidelity methods. Multi-fidelity methods are efficient, more efficient than stochastic hierarchy methods in some case, and they does not suffer from the curse of dimensionality. And the point is that multi-fidelity methods are also non-intrusive, whereas stochastic hierarchy methods are highly intrusive. So we need a dramatic we have to recast the model in a stochastic hierarchy framework. Lastly, I would like to introduce today the new class of methods that is called DSMC stochastic hierarchy methods that make use of the powerful technique of direct simulation Monte Carlo in the phase space and of stochastic hierarchy methods in the random space. With these methods, we are capable to guarantee spectral accuracy in the random space and to preserve the main physical problem of our the physical properties of our problem. So here there are some, I cited some works. It is a partial list, of course. There are many. I would like to mention in particular the school of Shijin, the results that he obtained with Jingwei Hu, Liu Liu, Yuhua Zhu, and collaborators. For this last part, so the SMC stochastic hierarchy methods, these are methods that we obtained with Jose Carrillo and with Lorenzo Pareschi. Okay, so let us go back to the SMC methods just for 1 second. Now I would like to set up the problem for variable Dal sphere. So for variable Dal sphere case, the interacting kernel reads as follows: in absence of uncertainty, it depends only on the relative velocity. So from the numerical point of view, we have to rewrite the collision operator, introducing some cutoff. So an upper bound that is here sigma. So for a fixed sigma, we consider the new homogeneous problem that is written here. So the gain part is modified as P, and the loss part is the usual one. And P is written as follows. So it is the gain part of the collision operator and this new term. Okay. Now, in presence of uncertainty, how can we perform the SMC methods for variable Dal sphere molecules with uncertainty, of course? So we rewrite our binary collision terms as follows. So the update of velocities is written as follows. So if we introduce a random number Xi, it's a random, uniform random number between 0 and 1, and then we rewrite the acceptance rejection collision process as follows. It is a totally equivalent reformulation of the binary collision term that I presented before, where psi is an indicator function. And now we have to evaluate the kernel for the two colliding particles. Okay, so once we have this reformulation of the velocities change, what we can do? We can project the velocities in some polynomial space. So we do as follows. We use a generalized polynomial chaos paradigm. So we approximate the velocities as follows. So they are the sum of some projection in the polynomial space multiplied by a polynomial term that depends on Z, only on Z, and the phi are a set of orthogonal polynomials with respect to the distribution of Z. V hat is as I said, is the projection of the velocities in the polynomial space. So V hat reads as follows. So it is the integral of the velocity multiplied by the polynomial term of order M, and on the multiplied by the distribution of Z. So it is the expected value of the velocity multiplied by the polynomial of order, the polynomial term of order m. This is very classical. So if v is sufficiently regular, this approximation, I mean, is not a problem, and we get spectral accuracy with respect to the random term. So it is very classical, and we would like to mention in this context the book of Lorenzo Pareschi and of Shijin, where we have, I mean, several kinetic problems solved through stochastic hierarchy methods. So a difference with the usual stochastic hierarchy approximation, here we are projecting not f, but the velocities of the colliding particles. So what happens to the binary interacting term? So we have to perform the stochastic hierarchy expansion for the binary colliding particles. So what we get is a collision in polynomial space. So from the term that I've written here, v prime I, v prime j, we obtain v hat prime of order m and v hat prime j of order m. And here we have to introduce these two matrices that depends on the acceptance rejection process, of course. And the other part is the usual term. So the above quantities can be computed using, for example, a Gaussian quadrature with h points, so that the computational cost of this process is m dot h, where m is the order of the GPC expansion. Okay, once we have the projection of velocities, now the point is to reconstruct the distribution function. So how to do that? Well, we apply the usual methods, so that from a Monte Carlo sample, we can reconstruct f, we can approximate f through a reconstruction as follows. So f that depends on z, on the velocities that depends on z itself, reads as follows. So it is a sum of Dirac deltas, but in the stochastic hierarchy framework, now we have just an approximation of the velocities, so that we have to sum the Dirac deltas centered in the velocities of order m, so that we have the approximation of the velocities. So the new quantity, the reconstructed quantities, is indicated by f n m, so that m is the order of the GPC expansion. What happens to the observable quantities? So we introduce a test function, and so we denote any observable quantities as the integral of f against the test function. That's very classical, so that the evaluation of the test function on the sum of Dirac deltas, so the empirical measure, is the sum of the test function evaluated on the particles, and the evaluation of the test function on fnm is the sum of a test function evaluated in the approximation of the velocities. Okay, now the point is that how can we guarantee that we approximate in this way the original solution of the Boltzmann equation? So can we construct some consistency estimate? Well, the answer is yes. Of course, we have to introduce a suitable space where to work. So we introduce this norm that is written here. Essentially, it is the L2 norms, both in the random space of Z and in the space of velocities. And we can prove the following theorem. So if the velocities, if the sample of velocities depends on Z and are sufficiently smooth, so in particular, this requirement holds, where H is the subwhole space. So what can we prove is that we can approximate observable quantities. So the difference on observable quantities is less than the Monte Carlo error. So n now is the number of is the sample number of velocities, so that it decreases as the usual Monte Carlo error. But regarding the the uncertainty part, so the part in Z, we decrease spectrally, and it depends on the smoothness of the velocities, how much we are smooth in terms of Z for the velocities. Okay, that's good. If we would apply just a Monte Carlo methods, so Monte Carlo in the phase space and the Monte Carlo in Z, we cannot have this order of accuracy, and in particular we are spectral in terms of Z. That's good. Okay, now I show you some example. So as you know, in the Maxwellian case, we have some reference solution. So let us suppose to have just a 1D uncertainty. So gamma, now the gamma enters in the kernel is equal to 0, so that the kernel is 1. And we suppose to have an initial datum with uncertain temperature. So the initial datum is the following, and T is the temperature. It is 1 over alpha, and alpha depends on Z. So we know that the exact solution of this problem is present and is given here. It depends, of course, on alpha, and so that Z propagates in time. And we consider alpha of this form. It is equal to 2 plus kappa dot Z, where Z now is a uniform random variable, just to make an example. Okay, so what happens, we can approximate the distribution function. We have here the distribution function, the exact one in the top row, the expectation at time 0, the expectation at time 5, the variance at time 0, and the variance at time 5. And on the second row, so on the bottom row, we have the reconstruction through the method, the SMC stochastic hierarchy method. So we approximate, of course, the initial value, the initial distribution correctly, and then for large time we have a correct description of the Maxwellian, the emergent Maxwellian, and the same for the variance. Okay. It has been obtained with 10 to the power 6 particles with an order in Z, so an expansion in Z of order 5. Okay, what happens in terms of convergence in Z? So we have proven that the consistency behaves like 1 over m power r, where r is it depends on the smoothness of the velocities. So we can expect spectral accuracy. So that's what happens. We block our collision tree at time 5. And for 2k that enters in the definition of the temperature, we measure the L2 error for an increasing degree of m. And what happens is that we maintain spectral accuracy so that we go to machine precision with a finite number of projections, and in particular with 10 projections, more or less, we are around machine accuracy. The same we can compute the first non-conserved quantity, that is the fourth order moment, and we have in the I norm at least a good precision in approximating this quantity. The same can be obtained in the variable sphere case. So gamma, even if gamma is not equal to 0, we have good results. For example, we can measure what happens in terms of the stress tensor. For the stress tensor can be computed exactly for Maxwellian's particle. So we computed in the variable R-sphere framework the evolution of the stress tensor, and we get these results, so they are consistent. And for an increasing gamma, so if gamma goes from 0 to 2, we reproduce correctly the behavior of the stress tensor, and in particular we have this order here that is sketched here. So for gamma equal to 0, we have this line, so that it is the top line. For ultra hard sphere, we have this second line here for the stress tensor, so that it evolves more in a different manner. In particular, they are quite ordered. It is very classical. It is a qualitative test, but it is very meaningful. In this test, in particular, we consider the 2D random variable, both in the initial temperature and in the gamma that we are interested on. And gamma varies from 0 to 2 in this test. And in particular, we have this variability zone in the evolution of the stress tensor. Okay, the same results on the convergence here that has been presented in the Maxwellian case can be obtained in the variable R-sphere case. We have to pass through a regularization of the step function, and that is coupled with a thermalization process. But in any case, we have qualitative results that are consistent, plus spectral accuracy in the random space, as in the Maxwellian case. Okay. A recent interest, I mean, a step forward, the comprehension of the inhomogeneous problem is presented by plasma dynamics, so that we are now working on plasma dynamics, and in particular, we have again the collisional framework. We add the presence of the electric field, where the electric field is given as by the potential phi, and phi solves the Poisson equation. Here we suppose to have a background of ion that are, that does not move. So in this case, we can reproduce the Landau damping in the non-collisional case, and in particular here in the top row, we are in the linear Landau damping, so that we reproduce correctly through all the methods that I presented before. The damping of Landau in the linear case, and the same for the non-linear Landau damping. Furthermore, here we suppose to have an initial datum with that depends on Z, and in particular the wave frequency depends on Z. So in the second row also we have some tests on the two-stream instability. And also in this case, through the SMC stochastic hierarchy methods, we are capable to reproduce the two-stream instability, and the results are consistent with known results. Okay, so it is an ongoing project, this one. Okay, in recent years, all the technologies that have been applied, that have been constructed for kinetic equation, has been applied to new phenomena, in particular in biology, robotics, and social sciences. And the point is that through kinetic equation, we have the opportunity to have a precise insight on the macroscopic dynamics of our phenomenon. So here there are some examples. So the point is that from binary colliding particles, we go through the description of large interacting set of individuals, like, for example, swarming behavior, traffic dynamics, pedestrian dynamics, and more recently, epidemiology. So what's the role of uncertainty in all these phenomena? The point is that the interaction rules now are no more physical, in the sense that we cannot have we cannot be certain about the interaction between agents, and it is an old question from the book of Prigogine and Herman in 71. So the interaction forces are not universal like the physical ones, once we consider interacting agents. So we have to introduce some uncertainty and to get some statistical information on the modeling parameters, so that we can get some robust prediction. So there are several works in this direction. Here there are a bunch of them. Of course, it is an ongoing project, and in particular, so okay, I would like to mention in this regard the work of myself with Jose Carillo and Lorenzo Pareschi, where we started actually the construction of Monte Carlo Galerkin methods. Okay, in particular, I would like to focus our attention today to kinetic models in epidemiology. Why? Well, the reason is pretty clear. I mean, it is a new process. It is interesting, and we have some data in this for this process. So the idea is to develop some kinetic model in mathematical epidemiology. Why? Well, actually, because epidemic dynamics can be taught as a multi-scale process, and individuals may transmit the infection or not. For COVID-19, the point is that the transmission of the infection depends on the social contacts of individuals. So people with a high number of contacts, of course, are capable to transmit the disease more than people that are closed in their own house, of course. And furthermore, the collective compliance with non-pharmaceutical intervention are essential to guarantee public health. Okay, so the starting point was this work by Bereau and collaborators, where a test has been done in, an empirical test. They measured the contact matrix of the French population, at least of a subset of the French population. And the point is that the density of contacts of people follows a gamma density. So it is no more a Maxwellian like in the classical kinetic theory, but now we have to reproduce some gamma density. That's the idea. So how to do that? Actually, we had this idea, so in collaboration with Giacomo Di Marco, Giuseppe Toscani, and Benoit Pertam, we introduced this prototype kinetic model for epidemiological dynamics, and we denote by Fj the distribution of the number of social contacts of the population belonging to some epidemiologically relevant class. It is called here J. J, for example, can be susceptible, infected, and recovered, but it can be also more complex. We can have also more complex compartmentalization of our population. So the sum of all this distribution function is given by F, and F is a distribution, is a probability function. So the integral of F, of course, is 1. Now, X is the number of social contacts. So the number of social contacts, of course, depends on Z. We cannot be certain, and we will discuss later on what is this Z. So the quantities, the aggregated quantities, the mass of Fj is given by simply integrating Fj with respect to X, and the higher order moments are given by Mj alpha. So the moments of order alpha are given by the integral of X power alpha Fj. So that's very classical. Okay, once we have introduced this modeling framework, we can study the following epidemic model of kinetic type. So we study the evolution in time of the distribution of contacts of susceptible, infected, and recovered that depends on the creation of their own contact distribution that is given by a thermalization process, here given by Qs, that depends on Z, of course, and some local incidence rate that is given by kappa. So kappa is the function that determines the transmission of the infection. Of course, if an infected person has many contacts and meets another person with many contacts, they have high probability to be infected. So the local incidence rate can be sketched as follows. So it is Fs multiplied by the integral of K that depends on the number of contacts of both interacting agents multiplied by Fi, where K is the contact function and depends on the number of contacts of susceptible and infected. So it is X to power alpha, Y to power alpha. Beta is the classical contact function. So the SIR model, the classical SIR model is recovered with alpha equal to 0, actually. Okay, if our alpha is equal to 0, we integrate and then we get the classical SIR model. Here we have the clear dependency on the number of contacts. So regarding the thermalization, well, we introduce a couple of them. It can be a Fokker-Planck type thermalization. The Fokker-Planck type operator that we can consider is the following, so that the equilibrium is given by the gamma densities. And this choice is coherent with the experimental one. As I said before, the contact distribution is of gamma type, or a BGK type operator, so that we impose the equilibrium that we desire, and so that we have a relaxation toward the equilibrium that is prescribed a priori. So we have classical analytical results in this regard, so that if Q is a Fokker-Planck type operator, then we have that if the initial datum is L1, then Fj is non-increasing. As a result, proving this theorem, we have that if the initial condition is L1, it is positive, then for later times, the solution of this Cauchy problem remains positive. And furthermore, after this corollary, we can prove the uniqueness of the solution of this Fokker-Planck type problem under suitable assumption on the contact function K. Okay, now how to compare this model, a kinetic model, with data? That's the point. So we have a kinetic model, and then we have on the other side data, and then we have to match the two points. Okay, so for epsilon, it goes to 0, and in particular, it means that we have a faster adaptation of individual social contacts with respect to the epidemiological dynamics under the assumption of symmetric interactions. We get, for example, for alpha equal to 1, simply integrating the system 2, and we see actually that the compartment of susceptible, for example, depends on the mean number of contacts of both susceptible and infected. It is very coherent, so that the incidence rate is now the highlighted one. So it is a new incidence rate that depends on the mean number of contacts. Okay, but now the point is that the system is not closed, because we have to find an evolution of the mean number of contacts. How to do that? Well, we apply usual strategies in kinetic theory. So the evolution of the first order moment depends on the second order moment. That is a conserved quantity for the Fokker-Planck operator that we introduced before. And then we can plug the equilibrium inside this integral, so that the second order moment can be written in terms of the first order moment. That's the point. So we obtain the evolution of the first order moment, so the mean number of connections that is given by the system 3. Now all the quantities depends on Z, as I said before. So why this number depends on Z? Well, because we collaborated a bit with the Lombardy region, and we discovered that the recovery rates, well, are not numbers, actually. They are distribution. Because, for example, if we subdivide, in this case, we consider the population of Pavia. So we subdivided the population of Pavia in several age group that is given by the Lombardy region. So it was not our choice. And then we measured the recovery rates that they gave to us. So we discovered that we have this distribution. So the recovery rates are random variables, beginning, for example, in all cases from 5 days, and it ends up to day 60 for people over 75. And in particular, from this distribution that are of beta type, we have an information on the mean recovery rate that depends on the age class. So we can consider gamma of our problem as a random variable that depends on the age group. Now, with the model that we consider and with the information on the recovery rates that we obtained on the field, what we had is a good agreement of our model with respect to available data in a 1 week or 2 weeks frame intervals, and how he enters, how the how the variability on the recovery rates enters on a decision process. Well, actually, we tried to simulate a vaccination strategy. Here we were 1 year ago, so we were really at the beginning of the vaccination of the European population. So we tried a couple of strategies. The first one is age decreasing strategy, so that we start with people that are with older people, and then we go backward up to the young people. And the second strategy that we tried is to look at a uniform strategy, so that we pick at random people of any age and then we vaccine them. So as a result, what we get from the variability on the recovery rates that we measured on the field is that the total number of infected decrease faster with a uniform strategy. But on the other hand, if we look to the total number of hospitalized people, we have the opposite process, so that with a uniform strategy, we have a higher number of hospitalized. And this information comes actually from the variability on gamma. So as you see, people with of the group 75, they recover after, let's say, in average after 21 days. So that if we adopt a strategy based on, an age decreasing strategy, they are more protected, so that the hospitalization decreases more faster than the hospitalization of a uniform strategy of vaccination. So just to show you that uncertainty quantification for kinetic equation has many applications that enters in many fields, and not only in the ones of classical physics. So what we did is to construct new numerical methods that is capable to preserve physical properties of the numerical solution of kinetic equation. And then we applied these methods not only to classical kinetic problems like the ones of, Boltzmann type kinetic problems, or the problems coming from plasma physics, but then we applied also this strategy to new models coming from mathematical epidemiology, for which we have a large amount of data, thanks to the collaboration with the Lombardy region. So the ongoing project, regards the non-homogeneous case for kinetic equation, so in particular for Boltzmann type kinetic equation, and we want to obtain hydrodynamic limit from this equation in the case of uncertainty, so that what we obtain is an approximation of Euler through Boltzmann, and that does not suffer from the loss of hyperbolicity of the application of stochastic Galerkin on Euler equation. So that's the program, and I would like to thank the audience, and I finished.
Thanks, Mattia, for this interesting talk. Do we have any questions? Please.
Maybe a modeling question. I think it applies to all the models you presented, that it always you have a certain uncertainty, but the uncertainty always affects the whole population or the whole ensemble of particles, right?
Yeah.
you don't know what the properties of the particles are, but what you assume is that all particles have the same.
Yes, indeed.
Right? Is that true?
Yes, it is like that. I mean, the particles here, it is a sample from a distribution function, so that, I mean, they suffer from the same uncertainty, since the uncertainty is, let me show you. Okay, the uncertainty is on F, for example, on the initial datum, so that the uncertainty is transmitted on the random sample that we want to consider for our Monte Carlo method. It is the same, of course.
Yeah, but the issue is that the dynamics is not really stochastic, right? You choose a certain Z randomly, and then the process runs, right, for this Z.
Well, Z does not evolve in time, so that, I mean, it is not a stochastic process. It is a random quantity. For example, measurement errors, something like that.
Yeah.
So it does not evolve in time.
Just to understand.
Yeah, yeah.
Any other question?
You said that you had this, you mapped the data of Lombardia to your model, but in the model there was no vaccination, no, so far at that point. Maybe I missed it, but.
Yeah, I mean, the point is that it was the second wave in Italy, so that we had no vaccination, essentially. So it was just a forecast. So here,
strategies of the vaccination.
so here, I mean, I presented the model with vaccination, but I didn't define it mathematically because, I mean, I had no time. But we have to modify this model, of course, to take into account vaccination. Here, essentially, you have an additional term that is a loss term, so that the mass is reduced by the number of vaccinated people.
And could you explain again these operators QS, QI, and QR? What is the sort of the? I missed the definition maybe. And
so Q is some operator, so that for epsilon that goes to 0, we have to get the experimental distribution function, it is gamma. So our proposal was to just take a Fokker-Planck type equation of this form, so that the equilibrium is a gamma density.
so
Otherwise, I mean, it looks complicated, but I mean, the equilibrium of this Fokker-Planck type equation is gamma. Otherwise, just take a BGK, F infinity is a gamma that you want. It is an experimental gamma, and that's it.
But in the epidemiological model, it does what precisely? What is the real life corresponding process?
Sorry?
The QJ, let's say, what does it correspond to in real life in your epidemiological model? And what is the epsilon?
I mean, the epsilon is the rate of adaptation of social contacts with respect to the epidemiological dynamics. And the point is that we don't know the transient regime, but we know the equilibrium, that is what we observe, and what we observe is a gamma density. So this Q here must be coherent with the description of a gamma in the limit epsilon that goes to 0. So for equilibrium densities.
I rephrase the question, maybe, you know, that. So is this kind of social interaction effects which leads to a certain distribution, what this QS, QI, QR describes? Well, I mean, what is that? What kind of dynamics is it?
The microscopic dynamics.
Is it like a social interaction, or?
Yeah, they are social interactions, so that you want to reach a target number of contacts every day, and you get this Fokker-Planck type operator. So it is, I mean, in the reference paper, we introduced a microscopic description, and then we upscaled to obtain a Fokker-Planck type operator, but I mean, for time reason, I avoided to enter too much into details. In any case, the point is that we want to go to a gamma density. Of course, there are many ways to do that. It is not unique, but the equilibrium density should be the same.
Okay, any other question? If not, let's thank Mattia again.
Thank you again for the invitation.